Hi everyone, we're continuing with the um, replication files for Baller et al. Now in R, picking up with the spatial weights, or the construction of spatial weights. First, I just wanted to point out that on Blackboard, in the replication files for Baller, um, after the article, um, our blog discussion, the replication assignment, the folder containing all the data, and the Geoda replication videos. These are the R materials down here. This first file is the first R script. So you can download that and then open R and then open this script within R. And then this is the first video that I'm building on now with this second video. So in the first video, just to recap, we covered some introductory steps, some helpful commands, how to install packages, how to open the packages with the library command, how to set the working directory, how to load data then with the read shape spatial command, and how to plot, to do some basic plot shapes, including a command or a set of commands to include more than one plot in the same graph frame. So we stopped with before we began this section on constructing spatial weights, so let's start right there. So if you'll recall, Baller et al., the analysis in Baller et al. Is based on a 10 nearest neighbors spatial weights matrix. So we'll skip straight to that. However, here you'll note that I've included some other specifications for some commands for creating a queen1 contiguity file, the rook1 contiguity file. We'll talk about these commands more in class. But then here are the nearest neighbors commands. And then I've also created some distance-based weight matrices, command for point data, and then a set of commands for standardizing your weights matrix, and then finally an inverse distance weighting setup for the command for a spatial weights matrix. So let's just focus on the nearest neighbors, specifically on the 10 nearest neighbors, but we'll do one other, the one nearest neighbor, just so that we can quickly see the difference. So let's first extract the coordinates from NAT. So we'll do that by creating a new object, chords. Again, you could call this object anything you want. Chords is constituted by, that's what this back arrow says, the command coordinates, the function coordinates being executed on the shapefile NAT. So that's going to extract the coordinates. So let's run that. I'm just jumping right in because I've installed and opened all of my packages. Then we want to extract the unique IDs from the data frame. That's what this command does. And then let's create a spatial weights matrix based on just the single nearest neighbor, one nearest neighbor. So we're going to create this object, national underscore one nearest neighbor, out of this function that finds the k nearest neighbors. It's going to grab those nearest neighbors, the one nearest neighbor, out of the coordinates data using the unique identifier row IDs. Right? So let's find that one nearest neighbor, and then let's jump to the 10 nearest neighbors. Right, in between is 5 nearest neighbors, but we're going to skip that. We're just going to generate the 10 nearest neighbors. So now on the left, you'll see that we have no errors. Everything's come through cleanly, and we've generated a one nearest neighbor spatial weights matrix and a 10 nearest neighbor spatial weights matrix. It's the second one that Baller et al. Use in their analysis. So now using the command here to generate more than one graph, right? Let's skip down one segment here. This command says that we want to create a new graph frame with 2 rows and 1 column, And in the first row, we're going to put the one nearest neighbor, and in the second row, we're going to place the 10 nearest neighbor. So we can run this all at once, highlight it, and hit Control R. And this is what it looks like. And just at first glance, right, looking at this very quickly, even a cursory glance here tells us that the top plot is not quite as dense as the bottom plot, right? And that makes sense given that the connectivity matrix for the top plot is based only on the single nearest neighbor, right? So for any one county, you're finding the nearest county, and that's the only one you're saying that the first county is connected to. Whereas in the bottom, for any one county, you're identifying the 10 nearest counties, and you're connecting that county to those 10 nearest counties, right? And those connections are depicted by lines. So we could expand this a little bit just to take a closer look. And here you see, right, that for any one county, you're finding the closest county, and so every county is connected to at least one, right, its nearest neighbor. But out here, you can see that it's much denser. And then if you have 10 nearest neighbors, then it's really dense. Right, so let's minimize this again. We could even close this. So now we've generated our 10 nearest neighbors. We might, that's a neighbor matrix for most spatial statistics functions, spatial regressions in R. You need to turn that neighbor matrix, that square matrix, you need to turn it into a neighbor list. And so you do that in this section here with this command here, which takes it's called a neighbor to list W, takes a neighbor matrix and turns it into a list object. Right? So for instance, our 10 nearest neighbor one is here, right? This is our 10 nearest neighbor matrix, and we're going to perform this function neighbor to list on our neighbor matrix to create this list object, which I'm just calling national 10 nearest neighbor underscore W to indicate that it's a weights list. It's a list object. Again, most spatial functions in R require a list object, so it's not enough just to create the spatial weights matrix, you need to convert it into a list object. So that's what this does here. We're going to highlight it in Control R, and then we can just summarize it quickly. You can see that there are 385 units. The number of links among these units is more than 30,000. You have almost 31,000 links among the 3,000 counties. Average number of links is 10. That is because you're finding the 10 nearest neighbors, right? So we could have gotten to this number, 3850, just by multiplying this by 10, because we've told R to generate a weights matrix with 10 links for every county. And that's it. So we could also, just to contrast this, we could look up at the nearest neighbor nat 10NB, and let's just quickly see what that looks like when we summarize it. So here you see that it's a non-symmetric neighbors list, and this is also a non-symmetric neighbors list. Weights style W, and that tells us that it's a weights, it's a list object, whereas this is a neighbor matrix. If we wanted to force this into a symmetric list, we could do so. So this is the command we just executed, turning our weights matrix into a list object. Here I've highlighted this section to create symmetric lists. So here we do this by, here's a 10 nearest neighbor. using this command, make symmetric neighbor, and then turn it into a list, right? So we want to create a neighbor weights matrix, a symmetric one, and then turn that into a list. So let's execute that, and we could summarize it. You can see here that whereas previously it says this is a non-symmetric neighbors list, that is no longer the case. It has, in the process of making it symmetric though, it's added more links, right? So now we've gone from almost 31,000 to over 34,000, and from an average of 10 to an average of 11. We can make that into a list object, and there we go. And now we see again we've got our same total number, and whereas before it warned us that this was a non-symmetric neighbors list, you see that that warning is no longer there. So that's quite nice to have both a list object but also to have a symmetric list object. So that's how we generate spatial weights. I've included multiple other options in here, as I mentioned at the beginning. Queen contiguity, rook contiguity, the nearest neighbor specification that Baller et al. Use, distance-based weights, some commands that you could try out for point data on a different housing data set, and the inverse distance weighting, and then a command to create list objects out of your spatial weights, and then a command to help you generate symmetric weights. There are also a couple of commands in here for standardizing or creating binary weights matrices. We'll talk about that in class as well. But the main point is that there is plenty to experiment with and play with here. And the reason for that is that creating spatial weights is a key, crucial, core step in any spatial analysis. To do even the most basic exploratory spatial analysis, you need to first explicitly specify the nature of the spatial dependencies among your units of analysis. And you cannot do that if you cannot construct a weights matrix. It's very easy to do this in Geoda, just using the pull-down menus and the graphical user interface. It's a bit more complicated in R, but the nice thing in R is that you can generate multiple weights matrices at once, manipulate them, force them to be symmetric. You'll remember that in Geoda we had a problem with replicating one of the analyses or the regressions since the weights matrix was not symmetric. So here we can force it to be symmetric and then move forward with our analysis. So please play with all of these commands, and we'll talk about them more when we meet in person. Thank you.